Patience, patience. Oh my God, amazing. All right. Nothing can possibly go wrong now because the technology is working. So this is a little bit of a small, intimate crowd, so I will invite you to ask questions. If I don't, the talk is designed to leave plenty of time for that, or to leave questions at the end, so feel free to raise your hand. If I don't see you, wave it wildly. If I still don't see you, say something. First of all, I want to thank you for having me here. BSD was a huge part of my graduate school experience. I went to Berkeley. That's where I got to know Kirk and Eric. I married into the BSD family. I didn't realize that was part of my grad school plan, but it turns out it was. And then a lot of my early research when I was a young assistant professor was actually done in NetBSD. Now those youngins come along and they want to do stuff in Linux. I let them. But the people in my group who are doing security stuff still use OpenBSD. So thank you. I appreciate all the work you do. And this is a little bit of a homecoming for me. So this talk grew out of a workshop that I co-ran last year around April with some Google folks. So Dave Patterson and then David Bacon of Spanner fame and Karsten Binnig. And we brought together a bunch of hardware nerds and database nerds and threw them together for a week to figure out how on earth we're going to deal with the increasing scale of data that we're being overwhelmed with. And I learned a ton about it, but I spent a week and had to go to Germany to do it, and I'm going to try to bring you all up to speed on that in the next, like, 45-ish minutes. So, serious title there. Maybe not so serious. The talk is really about memory GPUs and AI, oh my, because this is what everyone's talking about. But don't worry, this is not a disguise for an AI talk. I will mention it on like maybe one slide. So huge thanks to Dave Patterson and Mark Hill, who are real computer architects. I am not. And I stole shamelessly from their slides with their permission. And then I'll get to a little bit of storytelling in a few slides. And helping me tell that story, one of my students, Shaurya Patel, went down a bit of a rabbit hole with me, and I will share with you that rabbit hole when we get there. So one of the things I teach my students is that when you write a research paper, you're really telling a story, right? So every paper is a story, because humans are like designed to listen to stories and narratives. Now, the fundamental story that we have in all sorts of different cultures is the fairy tale. So I literally make my students tell me what they're working on and what paper they're writing in the form of a fairy tale. So please join me in that little idiosyncrasy and let me tell you a story. So once upon a time, if you were building enterprise software, you built that enterprise software to run on big IBM machines. And then time passed, and then we learned to write enterprise software on mini computers. Who recognizes this? There should be some hands in the room. Thank you. OK. And we have some other ancient artifacts here. Then we learned to write them on workstations and PCs. It was a sad day when I had to remove Sun Microsystems from my OS course because nobody knew who they were anymore. Yeah, I was literally in the middle of a lecture. I said, and then this. And I realized that not a single student in the room knew who they were. That was really sad. Anyway, and then we ran them on like these high-end servers of lots of little workhorses. And then we run them on the cloud. And I'm pretty sure that somewhere you'll find enterprise software running on like IoT devices and earrings if you choose to wear them. So we've learned how to build enterprise software that runs on pretty much anything. So we're done, right? Nothing left to do? Well, maybe not. There's still a few problems we could work on. So there's always new features. Not all new features are good new features, but we try to do them anyway. One of my favorite mantras is just because you can do something doesn't mean you should do something. That often applies to new features. Security, I would tend to call it an impossible problem, but I think there are probably people here who work on it, so we'll call it just really, really hard. And then there's scalability problems. So I would claim that we've been doing new features for 60 years, and we know how to do that. Security, I think, is the Full Employment Act for security people, so we're not going to talk about that today. So instead, I'm going to talk about scalability. The other reason speakers don't wear masks is because we get dehydrated. All right. So we've had a couple, excuse me, we've had a couple of, frog, go away. Who invited the frog? Demon, yes. Frog, no. OK. So how do we deal with scalability? Hello. We all have lived through, maybe, that memory has actually gotten increasingly large, right? So when I was in grad school, if you had the 16 megabyte machine, you had the big memory machine. Yeah, things have grown. We also have seen the migration from hard disks to solid state, such that my own central IT department at the University of British Columbia, which has on the order of 60,000 students, does not use spinning media for anything. Everything is solid state. I was a little astonished, but there you have it. So we've made some real strides at dealing with scalability. So what comes next? And this is where I want to get into the rabbit hole that I went down. So the circles I hang out with seem to say this phrase all the time, like, applications are becoming increasingly memory intensive. And I have been hearing this for, 5 or 10 years now. And so I thought, surely there's data that will support this statement, right? Because clearly it's true, isn't it? Well, let me just tell you that neither I nor my dear friend Chatty, that would be ChatGPT, nor Gemini, nor my really smart graduate student who's been working in this area, nor Archive, nor Google Scholar, nor anybody could actually give me any real data that supports this claim. And yet, you will hear people saying it all the time. So I went down the rabbit hole. So here are some of the most often quotes that are used to justify this claim. So this first one is a paper from 2020 in Eurosys out of Google, and it's comparing two traces of real production workloads between 2011 and 2019. And they say that, the amount of data per cell, a cell is a cluster of machines, increased by a lot. And then in 2022, we get this statement that, the cost of DRAM is expected to rise to 1/3 of all the cost of our hardware. And then we get another quote that, in Azure, it's going to be 50%, or it is 50%. So I decided to try to find the data that justified these statements. And I'm going to share that with you. So here's the trace comparison. So on the left, we're basically showing you the fraction of the cell capacity on the y-axis and over time. And the big dark splotches here are the production workloads. Okay, so this is from Google. So those are the production workloads. And those really haven't changed much between 2011 and 2019. And so it doesn't take like a rocket scientist to see that the growth is entirely in the green. Okay? So what's the green? The green is the best effort tier. Well, what does best effort mean? It means I don't really want to pay for anything, but I would like to get my work done, so I'm not in the teeny tiny yellow tier. So the entire growth in we're using more memory are the people who don't want to pay anything. I'm not really sure this says anything about applications needing more memory. So I'm not going to blame the folks who wrote this paper, but I am going to blame all the people who cite it and use it as an excuse to say that memory demands have increased dramatically. Okay? So that was that rabbit hole. So, okay, let's look at the, the cost of DRAM is going to reach 33%. So where does that come from? So that's a study of Meta's data centers, or I'm sorry, Facebook, Meta, I don't know what to call them. They don't express time in years. They express time in what are called generations of their infrastructure. So the x-axis is a proxy for time called a generation that I could not map to any real dates. So here's how I did the mapping. Gen 1, Facebook opened its first data center that it owned and built in 2011. So before that, they had been leasing from data centers. So I'm going to assume, perhaps incorrectly, that that's their Gen 1. If I'm wrong and their Gen 1 is earlier, it's even worse for this paper. And then if you read the pros, they say, oh, and Gen 5 and 6 are future generations. OK, so what data do we really have here? What we really have is from 2011 until the paper was written in 2022, sorry. So we have 11 years. And the fraction of cost that DRAM comprises rose from 15% to 22% in 11 years. So it rose like 1% a year. Suddenly, that isn't painting a huge, compelling picture for me either. OK, well, let's look at the Microsoft paper. So Microsoft is writing a paper about the cost of DRAM. And they're quoting something that says 50% of the server cost in Azure, which, by the way, is Microsoft, is DRAM. Great. So clearly, there's some data to back that up. No, this is actually a news article from something called nextplatform.com, quoting a guy who is, in fact, an engineer on the Azure cloud, but, oh, by the way, is also on the board of these consortiums who are promoting these standards for building bigger memory machines. I know I've gotten a little bit cynical as I've gotten older, but I'm just going to shut up there. By the way, somebody said something about YouTube. Are these being recorded? Yes. Good. As long as you weren't hoping on getting any of the hyperscalers to sponsor you, we should all be in fine shape. OK, so the last quote is actually from another paper. And this one, does this look familiar? Notice what the x-axis is labeled in? But notice, we don't have Gen 1 to 6 now. We have an off by 1 error. We're Gen 0 to Gen 5. OK, but this is basically the same data that we saw before, which is that memory is increasing. But in fact, who knows how much it's really increasing? Because if you go from Gen 0 to Gen 3, we're back at this 15 to 21%. So we've only increased 6% in maybe 11 years. So I am totally unconvinced that, in general, applications are becoming more memory hungry. They might be, but I could not find data that actually convinces me of it. So what do I really believe? Oh, question, yes?
So I noticed these numbers are percentages of server costs.
Yes.
Do we have information about how prices per unit performance for the non-memory parts of the server have changed?
Yeah, so I tried to look at that. There's one paper, and I can't remember it off the top of my head. I'd have to look at my notes, that basically say that DRAM and CPU costs actually increased in parallel. But it's a great question, and if I were not too cheap to pay analyst reports, I could get their crystal ball predictions, because they never talk about the past. They usually only talk about the future. So I think there's a mystery here. Yeah? Oh, yeah.
So I'm old. I was building apps on PCs when they first came out. And so you're wrong. I think that when you pin this down to server applications and the sort of life cycle we've had around frameworks and thinner operating systems, thicker open source stacks, it's probably been stable-ish during that time frame. But like the timelines you're talking about, I think need to be anchored somewhere.
Absolutely. So you're 100% right. If we want to compare memory consumption today to when I was in grad school, because I'm old too, our high-end CPU server build machine, when we were doing the initial Berkeley DB development, was a 486 DX2. OK, so yeah, absolutely. If you want to compare it to what we were doing 10, 20 years ago, you're absolutely right. We're total memory hogs. It amazes me when I look at how much junk is going on my machine, and it's consuming all my memory. But if we're looking at I think if we're looking over the last 10, 15 years, which is when people have been making this claim, I think the difference is not quite as dramatic. So great point, yeah.
The question I had was, are there data that are corrected for application density? Like, we run a lot more things on one server now than we used to.
So I'm glad you asked that question. I'm so glad you asked that question. I didn't set them up for it, though. Let's think for a moment about how hyperscalers make money, right? Hyperscalers make money by running your and your customers and lots of people's jobs on their clouds. So if I have a machine that costs X dollars, and I can pack more of your jobs on my X dollar machine, I make more money. So depending on just how cynical I want to be, I actually think a lot of this stems from exactly the point you're asking about, which is if you're a hyperscaler, you want to pack as much stuff as possible into a single machine. And I'll come back to a little bit, some of the problems we have with that. And so this is the question I actually posed to my student yesterday. I'm like, is all this research about, we need more memory just because the hyperscalers want to make more money? And so are we really doing work in the service of like 4 people or 4 companies, maybe 8 if you want to go globally, as opposed to like the entire community and making the world better? And I don't know the answer, but I'm becoming a little cynical about it.
I have one more thought on this.
Yeah.
I think that the characteristics of how the users perceive the performance of their application and the effectiveness of paging systems and the I/O rates, there's a lot of relationships there. And so if people will tolerate I'm being swapped out quarterly, they'll tolerate I'm being context switched better because CPUs have gotten faster, and so the app took a second or 2, it's fine. I think there's something there as well.
There's absolutely something in expectations, and the hyperscalers have to live with that, right? They've got to meet their SLOs.
Even enterprise running on their own data centers.
Yep, absolutely. Okay, so here's what I believe, right? I believe that, Chatty and all her friends, i.e. Gen AI and LLMs, are going to consume as much memory as we can possibly give them for the foreseeable future. I don't think this is forever, but it'll be for a while. And so this is just, it doesn't matter, right? All you need to know is the y-axis here is exponential, and the blue line is basically how big models are getting, and a model getting bigger just means you need more memory. So if 1 billion parameters was good yesterday, 1 trillion parameters is good today, and a quadrillion parameters is good tomorrow, and we're going to scale your memory needs by as much as you want. So those applications absolutely need as much memory as you can throw at them. Now, I'm a database person too, right? Data's not going away, right? We create more data every day. Pretty much something like every year we create more than we've created in all the years before that. And now we have Chatty and friends generating yet more data. There's a whole separate talk I could give about the dystopian future where all the data is generated by algorithms that we don't completely understand. So databases, right, or anything you use to store data, those are going to grow, and we know that they work way better if you can store all the data in memory. So yeah, people do care about having enough memory to store all their data. Data's growing, so yeah, we actually need bigger memory stuff. So I do believe in those things. I'm just a little more cynical than I was about the hype that applications are in general becoming more memory hungry. All right, so let's figure out what we're going to do about this memory problem. So in 2018, Hennessy and Patterson won the Turing Award, and they described that we are in this age of, it's the golden age for computer architects. And so, if you build big enterprise applications, you think, oh, great, does that mean we're finally going to have really scalable SMMPs? No, that's not at all what they're talking about. What they were really talking about was the emergence of accelerators. And at the time, in 2018, they were talking about accelerators with a little a. So these are, things like digital signal processors, or encryption engines, or compression engines, or stuff like that. But fast forward 7 years later, and everybody's still really excited about accelerators, but they're really excited about accelerators that begin with a capital A, and we mean GPUs. They might be TPUs, whatever, but these are these massively parallel units that we want for ML, machine learning. All right, so what do we do with these big honking accelerators? What do we do with accelerators? What are our options? So here's kind of the landscape. On the x-axis here, we've got cost. And on the y-axis, we've got how applicable is something that you build. So at the bottom, it's very application specific. In the top, it's very general purpose. So if you talk to the computer architects and you say, what can you do for me in accelerators? They will give you pretty much two options, right? Option one is the upper left. Cheap accelerators that you can use for anything. And so this is things like computing CRCs, encryption, compression, stuff that is now built into many chips, right? It's integrated tightly into our actual CPUs. So that's one thing you can do. The other thing you can do is you can go really expensive and application specific, and you end up with things like GPUs. Anything here in the middle is hard, right? Because what you're saying is it's not cheap. There's a whole bunch of design cost, and it's relatively application specific. So there have been these enormous breakthroughs, right? Factors of 100 or 1,000 in doing things like SQL queries, very limited families of SQL queries, or doing genomic analysis. And these are amazing, right? You can build special purpose hardware that does this, but you're not going to sell it, online to anybody who comes along. You're going to have a couple of customers. So the middle area is really hard. So if we want to address, this need for sort of more memory and more scalability, what are our options? So I'm going to give us two strategies that we'll talk through in detail. So strategy one is, you know what? Everybody and their brother now has a GPU on their machine, right? And that's been true for a while, because remember when graphics processing units used to be designed for graphics? So you laugh, and I do too, but the architecture of the chips that are really good for graphics, fundamentally different than the GPUs that are being built today to do all this machine learning. So we still call them GPUs, because they are similar in spirit, but they're completely different breeds, right? These GPUs are designed for machine learning. All right, so if we're going to try to use those more generally, and I think this is a reasonable strategy, if you can make workloads that are GPU friendly, that would be a good thing. So let's actually look at what a GPU looks like. So to look what a GPU looks like, we're going to compare it to a CPU. So here's a big old fancy processor. And the key features are that it's multi-core. I'm showing 2 cores here. Maybe you have 4, 8. You probably don't have 5,000. But you have multiple cores. You have multi-threading on each core. And come on, fess up. How many of you, the first thing you do when you're performance tuning something, you turn off the multi-threading? Yeah, OK. And the other half that are too shy to raise their hands do it too. OK, so we've got multi-core. We've got multi-threading. We've got superscalar, so we can get multiple instructions going at once. And then we've got out-of-order execution, because who wants to wait on memory? Let's rearrange things and hope that we don't have a bug that destroys data. And then finally, because it turns out we like to deal with objects that are bigger than a native word size, we always build in some sort of fancy SIMD instruction that lets us operate on multiple data items at once. So that's, to a first approximation, what the processors that I know and love work like, and I'm guessing most of you know and love, and these are our friends. And now we're going to introduce the wily beast of the GPU. So the first thing we're going to do is we're going to say, so why do you do out-of-order execution? Well, you do out-of-order execution to get a little bit more parallelism and make things run faster. But that's not what we're going to do in GPUs. In GPUs, we're going all in on hyperthreading. So we're going to get rid of out-of-order execution. Think going from CISC to RISC, right? We're going to go for a really, really simple processor here. All right, so we've gotten rid of out-of-order execution. What do we do next? Next, we're going to look at the superscalar. Why do we do superscalar? Well, again, it's sort of a way of getting a little bit more parallelism. But we're going all in on threads. So let's get rid of the superscalar stuff. All right. And what we're left with is basically a really simple processing unit that we can hyperthread until we get lots and lots of those, and then we're going to put lots of those cores in a package, and we're going to build what we're calling a streaming multiprocessor. So, if you squint really hard, it's what we thought maybe we could do back when we were trying to build big, large shared memory machines. And the difference is that they really didn't care so much here about the shared memory aspect. I mean, yeah, they share memory, but it's a whole different ballgame. So this is what your basic GPU looks like. Now, why is this interesting, and what has it done to our expectations about how the world changes? So let me show you data, like actually real data again. So now we have real years on the bottom, not generations. These actually map to points in time. And we've got essentially the past 55 years and the next 5 years that we're going to describe. This is logarithmic, so these are just orders of magnitude here. So the yellow and the black dots show you how many transistors we pack on chips. And I forget which is yellow and which is black. Yeah, black are CPUs and yellow are GPUs. But the higher order bit of the black and yellow is that we keep packing more transistors on chips, and it doesn't matter what you're building. We just keep packing more transistors on chips. Great. Now let's look at the solid lines here. So the blue is your single-threaded CPU performance. So if any of you were with me during the heyday of Moore's Law, right, 90s to 2000s, it was great. Every 18 months to 2 years, you bought a new machine. It was twice as fast. And it cost about the same amount of money. We'll come back to that in a minute. All right, so we got between 10 and 20x improvement over a decade. Cool. Another 10 years, still mostly getting the same improvement, maybe a little bit slower. We get about 10x in that decade. And then we run out of Moore's Law scalability, and things kind of level off, and single-threaded performance is no longer growing, and we start seeing a lot more multi-cores. OK, cool. So remember, the key thing to remember is we're getting about a 10x improvement every decade. If you look at the GPU line, we're getting a 1000x improvement in a decade. Now, you might say this isn't fair because they're getting it through multi-threading, right? They're highly parallel. But that's kind of the point. That's what they want to do. And here's the truly remarkable thing. So I didn't understand this fully until last summer when I heard a talk from one of the folks at NVIDIA. The biggest performance improvement they get in the GPUs is when they used smaller numbers for floating point computation. Now, at first blush, this might seem mind-baffling because they're doing all this, right? They're multiplying vectors of numbers. That's what all these machine learning algorithms are. It's just matrix multiply. But it turns out that you don't need the kind of precision that you get with 64-bit matrix multiply. And so they started going to like 32-bit, or 16, or 8. And I swear to God, last summer, I didn't completely understand how they do it. They were talking about 1-bit representations to do these machine learning algorithms. Do not ask me to explain it. It felt kind of magical to me, but almost plausible. So it's a completely different way of scaling what we're doing. If they get it down to 1 bit, you might ask, are they going to be able to keep it up? And that's a great question. And I don't know the answer. But remember, the previous Moore's Law curve was double the performance every 2 years and keep cost flat. And that was what was really remarkable about it. The GPU market is growing very, very differently. So the data up until 2024 I got from Dave, and then I tried to update it for this year. And it turns out that NVIDIA has announced their next generation processor named the Rubin, after Vera Rubin. And the numbers in black are ones that I'm pretty sure about. The numbers in red were sort of my best guess that I could read out of the tea leaves about, they've started hyping it up. But the key thing to look at is that the bandwidth is 13 terabytes per second, which is amazing. The less amazing thing is how much memory you get, 288 gigabytes. So this is going to lead us to a real problem. How do you take advantage of terabytes of bandwidth when all you have are gigabytes of memory? And so what has happened is we've migrated from what I call the old memory, the old I/O bottleneck to the new I/O bottleneck. So again, if you're old like me and you hear I/O bottleneck, here's the picture you think of. DRAM fast, disk slow, boo. How do we move data around? That's where all the cool kids hang out because that's where the I/O bottleneck is, right? Others with me, this is what we spend our lives trying to optimize for. Yeah, okay. If you're more my kid's age, so you're a cool kid, like here's the new I/O bottleneck. Persistent disk drive and flash doesn't exist, only memory, and memory is slow. The new bottleneck is between the caches and memory. So everything in your life is going to fit on memory, and the problem is that the buses between memory and processors are really slow. Is that a hand? I can also repeat the question if you just want to yell.
No, I was just going to say that Netflix servers, most of the generations are constrained by exactly that memory controller bandwidth. We can't go any faster because we don't have any memory bandwidth left.
Thank you. OK, so that was also good. You gave me a chance to dribble water on myself, which made me really happy. OK, so why is this bandwidth, why can't we get the bandwidth to main memory? And so there's a couple reasons. One is, the controllers. But if you think about how things are built, right, you connect things with wires, right? And that is a fundamental physical limitation, right? So there's only so many wires you can run between like memory chips and CPUs and things like that. So if you were a hardware person and you were faced with this problem, here are the two techniques that you're going to use to figure out how to get around wires. And so this is called high bandwidth memory. So the first thing we're going to do is we're going to put memory chips on top of each other, right? Because then you don't have to run all these wires on the board. You're running them just vertically. And then the second thing we're going to do is we're going to actually mount them directly on the same substrate that we put the processor. So instead of having to use wires to connect them, we're still using wires, but they're basically VLSI wires through the substrate, not physical wires that you can actually pull out a magnifying glass and look at on the board. And so if you go back to the picture I showed you, right, these 8 stacks, that's what they're talking about, are these stacks of DRAM. Okay, and when they announce a new generation, what NVIDIA seems to do is here's the base generation, which will be called Rubin, and then they're already saying in 2027 there's going to be Rubin Ultra, and the Ultra is going to have 12 stacks. So you can expect to see the bandwidth increase by about 50%. I'm sorry, you'll see the data increase by about 50%, and we'll still have great bandwidth, but we still don't have a lot of data. All right, so the two things we're going to do is we're going to stack our DRAM, and then we're going to put it on the same substrate that we put the compute die. And most of the time, the compute die is your GPU. Well, 288, 400, that's still not a lot of gigabytes. So then what do is you hook a bunch of these things with their HBM up on the I/O bus, and now you've got sort of lots and lots of memory, more bandwidth than you know what to do with, and we still have a little bit of a bottleneck. All right, so now we have a whole bunch of high bandwidth memory. Well, we have some high bandwidth memory with great bandwidth, but not huge capacity. And the question for you is if you want to be able to leverage this, what do you do, right? And I think the question is, what things can you offload to GPUs? And you might say, nothing, they're terrible, they're awful. And that's my reaction too. If you want to do machine learning, they're great. But I think that if we want to be able to show the kinds of scalability that the hardware is offering us, we've got to figure out how to use the hardware. So your good idea goes here. I am open to discussion and suggestions. But I think that if you want really, really fast memory, that's your only game in town. All right. So what if I can't do that, and I just want more memory? What else am I going to do? So here's strategy 2. which has been around with us from the beginning of time. What do you do when you need more memory? Well, you just buy more memory. So, but what does strategy 2 look like in this world? So the problem is that we've got, in theory, we've got compute to burn, but that compute needs more memory. And in these applications where we're talking databases, machine learning, that's absolutely true. Is it true in enterprise? I don't know. Is it true in your private data centers? I don't know. But what do you do if you really would like more memory, and you would like it a little bit without having to buy CPUs to go with it? So this is where lots and lots of hyperscaler attention is being focused. And the research community is like playing along, because the hyperscalers like having the universities look at problems they care about. And so there's this new standard, CXL. It stands for Compute Express Link. And the idea is that we're going to use it so that you can share memory theoretically across a data center. I'll show you, we'll get to the architecture that does that. Right? So the problem that the hyperscalers are trying to solve, and they are absolutely the folks pushing CXL, is that they have a problem that they call memory stranding. All right? So you're a data center provider, and you've got two different jobs here, one of which we will fondly call the memory pig, and one of which we will call the compute pig. So our memory pig doesn't use all the compute on a machine, but it's happy to consume all the memory, and it would like more, but it doesn't get more. And our CPU pig needs all the compute, but it doesn't actually operate on a lot of data. So you've got unused memory there and unused compute there, and that is bad for a hyperscaler because that's low utilization. And so what you'd like to be able to do is, you know, as the game show says, phone a friend. Hey, you've got more memory. Want to lend it to me? How do we make that happen? All right. So CXL is actually three protocols in one, because if one is good, three is better. So CXL.io is basically fancy PCI. You know, how do you set up interrupts? How do you configure things? CXL cache is super exciting. CXL cache says, if you're an accelerator that has like a few gigabytes of memory or a few hundred gigabytes of memory, you can treat that as a cache for the massive memory pool out there. And the hardware will do all the cache coherence for you. Wouldn't that be lovely? Guess which protocol is not embodied yet in any device you can buy on the market? Cache. Coming real soon now to a chip near you. And then the third one is memory. And this is, so does anybody remember the distributed shared memory movement of the 1990s? Yeah, so love Kai Li, think he's fantastic. He invented it. It seemed like a wonderful idea. And the idea was you have a network of machines, and imagine that you could use all their memory as a big distributed pool, and it would all happen transparently. And we built systems like that in software. And those of you who weren't there, what happens when you do that and your memory is sitting on a different machine? Just take a guess. It's really slow, right? Networks, not so fast. OK, so distributed shared memory did not take off, but there were hundreds and hundreds of papers about it. You could go to entire conferences where a third of the conference was distributed shared memory. CXL is hardware-based distributed shared memory. And so the key thing there is you can use loads and stores to get data off somebody else's node. Right? Kind of a cool idea and implemented in hardware. All right. So if you go and look at all the fancy stuff, they'll tell you about 3 use cases. I'm going to focus on the rightmost one, which is you know, the solution to the buy more memory problem, right? How do I use this, the memory portion of CXL, to actually grow my system? Here's the way to think about it. It's another layer in the memory hierarchy, right? So you've got really, really fast cache. You've got local DRAM, direct attached. And then you've got remote DRAM. And this time, instead of going over like Ethernet, which is what we were doing in the 90s, you're going over your high-speed data center interconnect. OK, and then you get to SSD, and clearly CXL should be faster than that. All right, so how do we expand applications memory? So as I've been saying, you know, borrow memory from a friend. So that makes sense. The other thing you could do is you can just have memory nodes, right? just vast banks of memory, CXL controller in front of them, and now this compute node has, oh dear, it looks like a NUMA architecture. I have some DRAM that's really fast, and then I have some other DRAM that's not quite as fast. So all that work we did on NUMA, or maybe we didn't, maybe we should, I don't know. All right, so that's another architecture. Now maybe you just want big memory pools that you mix and match among machines. You can do that too, so you can do memory pooling. And let's imagine that that's still not big enough. Then what you can do is you can get a switch that talks CXL, and now you can essentially turn your entire data center into one big memory pool, right? And you can attach different kinds of memory here, right? You could attach DRAM. One of the really interesting use cases is you can also attach brand new shiny DRAM that's really fast and older DRAM that you would normally throw away. But if you're already dealing with NUMA and you've got different latency memory, maybe you can keep that old memory and reuse it. So there's a whole line of work. Perhaps some of the most exciting to me in the CXL space is how we actually make our data centers greener by reusing memory for longer. So that's kind of cool. Or wait, maybe we could put persistent memory. And then you'd have that as another tier. Oh, wait, no, we can't do that because you can't buy persistent memory anymore. Oh, bummer. OK, so just a little bit of a poll here. How many people were really excited about Optane and the thought that you could finally have technology that was as fast as DRAM and persistent? Like, I totally bought into it. I wanted this so badly. We were very disappointed. But here's the weird lining to the really ugly rain cloud. So I spent a bunch of time being very excited about persistent memory and trying to figure out how to make it work. And then I had this realization, which is like, let's imagine we really kept our data in persistent memory. What happens when your machine burns up? Now, admittedly, this shouldn't happen very often. But as somebody whose entire data center was flooded by the sprinkler system, bad things do happen. And if you have important data, you're not supposed to lose it. So I started wondering, like, wait a minute, if we're really, the beauty of disk drives and SSD, like, you can unplug them and you can move them, right? DIMMs, it's a little tougher to do that. So I started asking people, like, so if I really care about this data, I probably have to replicate it. And if I have to replicate it, like, how much benefit is it that I'm running at close to memory speed? Like, is that really a win? And so I kept giving these talks where I said, what is the killer app that is going to make this work? And that's exactly the response I got. So loved the concept of persistent memory, like thought it was just fabulous. But even before they canceled it, I started becoming worried that there wasn't a way to use it. And if anybody finds this interesting, talk to me at the break about the Konami bubble machine. And I'll tell you about how history repeats itself. OK, so quick digression there. Oh, wait, there's one more step we can go from 2B, which is we can have lots and lots of CXL switches. This is where you get your entire data center as a big memory pool. And then they give, this is so fancy, they call it fabric-attached memory. But it's just like we know how to build hierarchy, and that's all they're doing. All right, so that's the buy more memory approach. And so the question is, are there use cases for that in the things you're deploying? And I think maybe there are. There are CXL parts coming on the market now. But I think what it really means is we really do have to think about NUMA either again or finally, depending on where you ended up in that. All right, I am going to wrap it up there. Quick thank you to the NSERC, who's the Canadian National Funding Agency, who had the good sense to convince me to come to Canada 7 years ago. I'm a happy Canadian citizen now, perhaps happier this year than I was even last year. And thank you to UBC, who has been a great home until they made me a department head. Not happy about that. But mostly, I am grateful for the amazing students I have. many of whom are deep systems hackers, many of whom do other things too. I've never met a research problem I didn't like. Short attention span, research problem I didn't like, you pick. But they make everything work, and they get all the credit. And on the slide, I just want to pause for a moment and leave you with an observation and a plea. So I go to a lot of conferences. I've been doing this for a really big number of years. And walking in today was one of the less comfortable ones I walked into, because I looked around. There weren't very many people who looked anything like me. I understand it's hard, but not shown on this slide are my two awesome graduates from a year ago who were the best undergraduate kernel hackers I have ever had in 30 years as an academic. They were stunning, and they were both women, and they're rock stars. And they're now working at various companies doing great things. So we know they exist. They are existence proofs. Anyway, there's a lot of people who don't look like us that aren't in this room. So that's my observation and my plea. And this gets back to the opening, right? Attendance still isn't where it was. If every single person in this room makes it a conscious effort to bring a friend next year who doesn't look like you in some dimension, I don't care what the dimension is. I have a colleague with blue hair. I could bring her, right? Bring somebody who doesn't look like you, and we will all be better for it. So that's my plea, and I don't know what our time is. I'm happy to take questions.
So I'm going to go the, am I on? Okay. I'm going to bring in the AI specter.
Cool.
And I've actually given talks somewhat similar to yours, not quite as focused at the low-level memory architecture, but more at this evolution of computing. And so I was at the beginning of the PC era where PCs replaced mainframes. Mainframes had lots of peripheral circuitry around I/O and things like that, so that the CPU, which was not very fast, could do its tiny best and channel along. Punch cards have entered the chat. And then, my whole career has been defined by that sort of microprocessor von Neumann architecture and the memory bandwidths, and like Xbox, we sat down and the problems we had were all about memory bandwidth, right? And I look also at this era that has defined my entire career around what people call all the time digital transformation. And as someone living on the front of that, I always sneered at that term. And now I'm waking up to the fact that we're at the end of an S-curve where there is no segment of our lives that has not been digitized in some way. We are all increasingly, unfortunately, gig workers to some software system that determines what we do, even teaching. And Moore's Law has been dead for quite a while, right? It was never a law, it was always a goal at Intel. And so that sort of compute cycle has changed. And for better or for worse, we can look at the AI space and we know that half of the time, at least, they're hallucinating complete junk. But the other half of the time, they're doing some really interesting things. And it challenges what we think about in terms of what software development means, because the lifetime of a program used to be one of the most interesting attributes of a thing. If this is a long-learning service, we're going to have it around time, it's going to be maintained by engineers, we can do all the engineering practices. If I can tell an LLM to generate the program I need, and then next week I tell it again, it generates something functionally equivalent to that, and it's running in some cloudy pile of GPUs or TPUs or whatever, everything changes. Like how we think about software and how the energy goes in. And I also want to draw attention to like industry trends go where the money is. And the general purpose computing that was possible because of microprocessors drowned out anything you could do with much more custom design and carefully like that. And same thing for batteries and same thing for smaller, lower power consumption. Apple won on the AM circuitry because they focused on heat dissipation and power rather than raw throughput. And turns out those ended up being the bottlenecks down the road. And so I think your first strategy is actually the right one, but not how can we, doing normal von Neumann type architecture processing, go off and start using memory better, but more how can we realize that this is the next generation of computing and our CPUs will be relegated to the I/O processors of our mainframes. So it's not really a question, it's a statement, but I'd like to hear your thoughts on it.
Yes, this is our existential threat. Opportunity, great, yes. Point taken. So Wow, there are so many answers I have for this in so many dimensions. So I will do a random assortment, and then you just cut me off when I run out of random things or when you get bored, right? So, I got invited in the fall of 2023 to do a panel on Gen AI. And I was like, I don't do Gen AI. I don't do AI. I do a teeny little bit of ML. No, we really want you on the panel. We went back and forth. I agreed to do the panel, and I see their first description, and they say, 4 experts in Gen AI, ... I'm like, no, you can't say that. Then they changed it to, get this, 4 theoreticians. And I'm like, no, you can't say that either. We finally ended up with 4 computer scientists. So the thing that was remarkable about this is that I found myself on this panel, which I now fondly refer to as Margo and the Fanboys. And it was the first time in my career where people who I knew, respected, who I thought were really smart, had gone completely off the deep end on a technology. And then, fast forward a couple years, I find that I am actually married to somebody I know, like, respect, think is really, really smart, who's gone pretty far off the deep end on Gen AI. So I get pushed on this a lot. And there are a couple things I come back to. So one is code is not correctness. And there is nothing in the Gen AI stack that is designed to guarantee correctness. And we've come to expect certain levels of correctness in our systems. So I think that, if I build a GUI, which is something I've never built in my entire life, I have no interest in learning how to do it, but I am absolutely happy to ask Claude to help me do that. And if there's a bug in it, maybe I don't care. If it's my bank software, I think I care more. So I think, the position I tried to take in 2023 is that, these tools are tools, and they're going to be part of a much larger system. And we've seen that, right? They call it an LLM, but now what you actually have is like, ooh, this is a math problem. I'm going to ship it off to somebody who actually understands math, right? And so they're starting to build a system around this. We are system people, and so far, the tools haven't gotten anywhere close to really understanding how to do what I call system-level stuff. Will they or won't they? We can talk that for hours over beers anytime. I don't think it's obvious that we'll be there soon. Will we get there? I don't know. One of my former colleagues is at Sydney, and he's now he was one of our Sleepycats who built the Berkeley DB system. He was also then a Wired Tiger who built the system that underlies Margo DB. And he's now playing with Gen AI tools to figure out how much of the work can they do in trying to build a robust data storage system, right? One of the pieces of software that we like to describe as, when it fails, your customers have not only the desire to hunt you down, but the time, because you've lost their data. So I actually think there's a huge amount of work to figuring out how to use these tools to do the kinds of things, like the value we bring is not the lines of code we write, right? It's understanding how systems work and how to get things right. And I would like to believe that getting things that work correctly is actually important. I could be proven wrong. I don't know that I want to live in that world, but we'll see. So that's part of the answer. The other part of the answer is in my faculty meetings, every time we talk about hiring, and you might imagine that all the AI and ML faculty are like, we need to hire an AI and ML. Even though we have 50 people, we need 50 more. And there's a wonderful paper, I want to say it's from like 2010, and it's called, it's from Google, and it's called Technical Debt in Machine Learning. And see figure 1. And figure 1 is like a full, width of a page, and there's this teeny box in the middle that says machine learning, and everything else around it is what we do. It's system stuff. And there's another box that says feature engineering. We'll give them that one too. So I think that there's still the need for stacks. I think it's an open question how well these tools can help us. So on the top of my to-do list in my copious free time is some of the machine learning research I do. We have this big pile of C++ code that needs to be refactored, and it needs to be integrated with a bunch of new features. And I want to see if Claude can help me. So this is like my project that I am dying to find time to do, and if it works, I'll come back and report back. So long, windy answer, which is I haven't a clue, but I have some random thoughts. Yeah?
When you were talking about PC evolution in the 90s, you mentioned that should I come to you?
I'll run. This is how you get your exercise.
Thank you. When you were talking about PC evolution in the 90s, you mentioned sort of every 2 years you'd pay the same price for your newer PC, and you said you'd come back to that point. And it was really notable on the graph of, I think there were generations of NVIDIA architectures, how the price was increasing. Could you say more about that?
Yeah, so I don't have a great explanation, but you're right. I didn't come back to it explicitly, but when you look at the NVIDIA, right, we get a new generation every 2 years. Great. They're not doubling in speed. They're changing in all sorts of weird dimensions. And NVIDIA charges us more for them. How is that fair? So I think this is much more of a technical, an economic argument than a technical one, right? Which is that a bunch of companies did not see what was alluded to in the last question, the transition from CPU-centered computing to GPU-centered computing. And NVIDIA did. And they went all in. And other people didn't, right? So who would have thought that even 5 years ago, if it was the middle of the pandemic, 7 years ago, if I had come here and said, Intel, 10 years from now, they're going to be in a world of hurt, right? You would have laughed at me, right? Who would have thought that? But here we are, and NVIDIA is, the golden girl. So I think it's more about they can charge us that. And in the 90s, when we started seeing, right, there was actually a lot of competition in the chip market, right? In the 80s, we had the Motorola's and the Intels and all this other stuff, and then it became a monoculture. And by the time the monoculture really got established, the curve had started slowing down. So I think it's more about economics, and I won't even begin to try to talk about that. I faked it with the Gen AI, but economics is too far. But that's my guess. Any other questions? Yeah. I'm making him do as much running as possible, so then I'll come back down to the front.
Thanks for the presentation. I was just wondering, doesn't the memory sharing system over the fabric stuff, that CXL, doesn't that pose huge security questions about how data is shared across the fabric? I know you said you didn't want to talk about security, but
super great question. So I'm not the security expert. One of my colleagues, her main focus is side channel attacks. And so she has been looking at the CXL protocol and actually trying to figure out if there are vulnerabilities to side channel attacks. Shockingly, she believes there are and that they found one. It turns out it's really, really hard to get the right data. If anybody happens to have one of these really expensive $500,000 PCI analyzers, we would love to borrow it. But yes. And it's not, you can always encrypt the data when you're moving it around, but observability of the pattern is absolutely, possibly a side channel. We'll know more over the next couple years as people really try to figure it out. But yeah, you're 100% correct. And I think that's really true anywhere, right? So we can watch data travel across the internet and have side channel attacks there too, even if it's all encrypted.
I'm just going to pile onto that. Every CPU optimization you talked about in the first ones has resulted in nasty, awful security problems.
Yep. Absolutely. I have theories about how we're going to solve that, but they're a little crazy. So again, at the coffee break. And then there's a question in the front.
I was just wondering if you could speak a little bit more to the challenges of NUMA with CXL. Does that differ a lot from traditional commodity NUMA systems? Are there additional dimensions aside from just access latency that cause problems? Or?
So I think, at the end of the day, yes, you've got memory with different latency. So in that sense, it's exactly the same. I think the way it's different is scale. in that we can now have NUMA access and latency changes across a whole data center instead of within a single system. So I think that's a little different. And the other piece of it is that, and you run into this in a single system, but I think it just becomes bigger and more complicated, is when do I keep accessing the data remotely, and when do I actually try to move it between tiers? And so I think it's the same kind of problems. I just think we've made it bigger and maybe more complicated, but maybe not fundamentally different.
I was just wondering, I mean, yeah, is like variance of access latency more of a problem? Or is it going to be pretty consistent?
Yeah,
I have no
so
real interest.
I don't feel like I have enough data on the top of my head to answer that definitively. You know, clearly the number of switches you go through is going to add latency, right? And so as soon as you're talking about like a fabric, then you clearly are going to have different tiers, you know, multiple tiers within this thing, and more of them than I think you do in a conventional system.
So I'm thinking we'll know whether or not CXL is going to be a win when VMware implements it.
I mean,
'Cause
Broadcom.
Well, in the VMware product family, yes. I figure if they're implementing it, that means it's here to stay for a while. Of course, that leads me to my first concern is how long is it before Palo Alto releases a CXL firewall? The thought of which just sickens me, but you know, there you go. I'm sure it'll happen. It seems to me that would be actually one of the most easy wins for it. Is like I'm not a hyperscaler, I'm maybe a mini scaler, if you will, and like we migrate VMs approximately one every 2 to 3 seconds, all day, every day, to rebalance loads. And if CXL allows the memory of that running process to be accessed remotely, you know, hot migration just becomes a lot easier. They don't have to do all the state tracking and snapshotting of memory and all that stuff. You can just access the running space directly over the wire.
That's a cool idea. So I haven't heard anybody working on it, but that's actually a great application of it. I would love to see. That's a great idea.
Seemed obvious to me.
You think about different problems than I do. Yeah, no, I love it. That's great. I can admit a new PhD student now. Yeah.
Yeah, I just on hearing that, like, you do copy art, right, with it? But the other thing that occurred to me for CXL was I used to work at Pandora, and we'd have tiers of media servers for doing our serving. And the first tier was everything out of RAM on the local machine. And the second tier, we had very expensive specialized PCI Express cards that had a bunch of DRAM on them and looked like RAM disks to the machine. And CXL would be like the next generation of that technology. So
Yeah, instead of making them RAM disks, they're just
right,
more memory.
anyone doing streaming media would find those for like the high use pieces of data.
That's great.
Yeah.
Okay, so we're going to start our little CXL company after meet us in the lobby. All right, looks like maybe we're running out of questions or people need more coffee. Yep, all right.